All right, can y'all hear me okay?
Yeah.
All right, so let me get started. Just as a reminder, your chapter 28 homework, actually I think I give you guys another day for the chapter 28 homework. So it's due tomorrow night. I noticed hardly anybody started on the homework. Ohm's law is due on the 29th if, and one thing that's in the syllabus that says if the exam date and the lab date fall on the same day, you can turn the lab in the following class, the following day, which would be a Monday. So, I mean, you can, if you need the time, turn it in on Monday without the lab being considered late. Okay? So this is due on Friday, but if you need to, you turn it in on Monday. Well, I would try to get out of the way because you got this lab to do, and this is, has a lot of data analysis. Okay, even though the data collection goes quick. This Friday you have the exam, and then remember, from this Friday onward, all the Friday meetings are in person, so I'm not recording anything. Okay, so you just got to make sure you show up.
Hey, Professor, could I ask a quick question about turning in the lab on the following Monday?
Yeah.
So, like, how early can we come to campus and turn it in? Or, like, if you're not there, can we slide it under your door?
Sure, yeah, you can do that. That's fine.
Okay, cool. Okay, cool. Thank you.
Yeah. Usually I'm on Mondays, because I do my Monday lecture at 9:30. So I try to get here before that. I mean, it just depends on how early I can get here. But usually I'm here by 8:45. So, but if you get here before that, you can just slide under my door. That's okay. Other questions? And there have been questions on the lab, and students have found mistakes on my lab. I don't know if you've been following the Discord, but this lab used to be, the first part of the lab used to be on the DC circuits lab because the equipment we used on campus for the Ohm's Law lab was a little more simpler, a little more expensive. But when we switched to online, I had you learn how to use the proto board right away. And so this lab actually has an extra part to it, which is part 1. Okay, so you might see the part numbers in the analysis section mixed up. So just real quickly, in part 2, remember you're making the graph, delta V and I over here, and the slope of the graph is equal to your resistance. Okay, the slope of the graph is equal to resistance. So in part 2, you're going to report the resistance along with the uncertainty in the slope of the graph. That's the uncertainty in the resistance value from your data collection, and you're going to compare it to what you measured with the multimeter, and then you're also going to compare this value with the color code value. Okay. So you'll do that comparison. In part 3, you're also plotting delta V and I, and this function is not going to be a straight line. It'll be some curve. So please don't fit to a line. It's like every semester I have someone who fits it to a line, even though I say not to. It never fails. Okay. So you find the curve that best fits the data. I'll let you figure it out. I mean, different students will have different functions. That's okay. But you limit the amount of parameters. Don't give me a 5th degree polynomial. It'll fit fine, but then how do you interpret it? Okay.
Remember, I also had a quick
Go
I
ahead.
also had a quick question on that part. Just for the resistance of the bulb, like how significant of a difference are we supposed to see like before and after? Because I only saw like a difference of like 0.1 ohms.
Yeah, it cools off pretty quick.
Okay.
Yeah, and
Okay, cool.
with the light bulb, you see it a little bit more. But these cool off pretty quick, so you don't see much of a
Okay,
difference.
cool. Thank you.
Sure. And then I've noticed that on the last data point, some students have had issues for this one, and they might be reaching the limitations of the power supply. If that's the case, then, just write a note. Okay. I had a student who was getting, when they set the voltage to 12 volts, the current was 0. The light wouldn't even go on. And I think it's because that light bulb is causing the power, the multimeter, or not the multimeter, the little plug to go beyond its capacity. And you'll see the green light on the plug go on and off. Okay.
Yeah, I had something similar where my light would like flash on that last voltage.
So you're probably reaching the limit of it, and that
Yeah.
data is probably going to be bad. Then that data point will be bad. Probably not worth
Okay,
including it. So write a note in it. You can write in the figure caption that that's what happened, or write it below the table. Okay. And so then in the analysis section, or in the results section, it's going to ask you to write a conclusion. Basically, what you want to talk about is your attempt at interpreting the results. That's it. Try to put some coherent thoughts together. It's really all I'm looking for. Part 4 is going to be a little bit different. You're plotting, this time you're switching the axes. And that's because we have an equation. And I know this is not written correctly in the lab. I've had it like that for years. It should be delta V, not V. Okay, and so this is a fitting parameter. This is a saturation current. And that's a fitting parameter. See, in principle, this will be a number between 1 and 2. It might not happen in your case. Okay. And this is a very small number of the order 10 to the minus 7, 10 to the minus 8. And so you're gonna do a fit to this data. Don't fit the data for table. Do not fit to the part in table 4, because remember what I said in the lab for table 4. You need the microamp scale to do this one, where you take the diode and you just reverse it, right? You remove the diode from the circuit and flip it. And because you only can use a 20 milliamp scale, this thing will probably read, most of the values will be 0. And so to do a curve fit and including these points, when you're not using a multimeter that's good enough for you, it's going to mess up your curve fit. So when you do your curve fit, just fit to this data. In fact, what I would do is fit to this data first and then add these data points to your graph. Does that make sense? Actually, you don't have to do that. Cy Davis will allow, when you do the curve fit, Cy Davis will allow you to choose the range of values you want to fit to. Because you have to use a fit wizard. To do this curve fit, you have to use the fit wizard. And you have to have the software. You have to tell the software, I want to fit to this equation. Okay? Because you don't have that equation in SciMath. You have to actually type it out. So when you go to Fit Wizard, there's a selection for user-defined function. And then you can type that in. You have to define your own equation for this one. You might have done it in 205, I forget. I don't remember the labs you did in 205 in the online version. And again, in part 4, in the results sections, the analysis is just basically what are your conclusions? You just say, what were your values for I sub s and n? Okay. What does this say about the diode, right? I mean, remember, the diode is the device that allows current to flow in one direction. Okay. Questions on any of this? I'm going to try to send you one more revised version of the lab. Of the previous 2 semesters, nobody found mistakes, but you guys have been good at finding the mistakes in the lab, both classes. No questions then? We're okay? And you have the sample lab report to refer to. And those of you at Physics 205, the lab report should be of the same style as what as Physics 205. I might be a little picky on some things as compared to others. I mean, we all have things we look at more closely than others when we grade lab reports. So just do a good job in this first one, okay? Because you have 3 more written lab reports you're going to have to do. Okay, so today then I want to finish off RC circuits, and I'll spend some time on RC circuits. Usually I go through this quickly. I'll spend some time going through a couple of examples, and in fact, what I'll do is I have a couple polling questions to prepare for the exam, and then I'll do in the second half. I'll do the introduction to magnetism. So once I'm done with RC circuits, we'll take a break, and then I'll introduce magnetism. Okay, which will be our 4th unit already. Okay, and this will be chapters 29 through 31. None of this will be on the exam Friday. By the way, in the exam Friday will have 5 problems, and then some short answer stuff. You should go on Canvas. Actually, no, wrong. I emailed you the old physics department website. I emailed you actually the link to all my Physics 210. It used to be called Physics 4B a long time ago. And it has all my old exams there. Those are my sample exams, so go through them. And I think that exam has 5 problems on them, and they're nice and challenging, those problems, okay? So I would definitely go over them and make sure I understand those problems, all right, because they're fairly comprehensive. And they are challenging questions, at least I think so. So go over the practice exam. I think if you go to the old physics website, it'll be exam 2. And that's because we didn't do relativity first back then. Okay, so if you look at exam 2 on the old Sierra College physics site, and I emailed you the link, you'll find you can practice on that exam. Okay. Questions regarding the exam? All right. So a week ago, our last meeting, we ended up talking about RC circuits. And in fact, I ended up talking about the circuit in which the capacitor charges up and the circuit in which the capacitor discharges. So let's start by drawing the basic RC circuit. And we set up we apply Kirchhoff's voltage law, and we set up a differential equation, an easy one to solve, to determine the charge on the capacitor as a function of time. And the equation had that form where Q max is equal to the capacitance of this capacitor times the power supply voltage. And of course, This is the voltage across the capacitor when it's fully charged. When the charge stops flowing. Okay? And then we can also define the time constant tau just for fun, because then we can say, okay, how much charge is on the capacitor when t equals tau? Well, that makes this exponent -1. So I get 1 minus e to the minus 1 times q max. And so when you take 1 minus e to the minus 1, that's 0.63. So after one time constant, the capacitor has 63% of its maximum charge. Okay. Questions on this? Okay. And then if we want to find the voltage across the capacitor, then we take this equation and divide it by capacitance, and you get delta V sub C equals delta V sub R, delta V sub S times 1 minus e to the minus t over RC. And you can see as t goes to infinity, the capacitor voltage equals the power supply voltage, and then the voltage across the resistor is 0. If I want to find the expression for the voltage across the resistor, I'm going to use the current rule, or the current law. The voltage across the resistor, or the voltage drop across the resistor, is equal to the voltage drop across the power supply minus the voltage drop across the capacitor. And this is just going to give me delta V sub S e to the minus t over RC. Now, of course, there's another way to determine this, because the voltage across the resistor can also be written as the current through the resistor times the resistance. So how do I get the current? Well, I take the time derivative of this expression. If I take the time derivative of this expression, I'll get and then I multiply this by R. So notice I could have gotten that equation easily using the voltage law, Kirchhoff's voltage law. Okay. So these were the main equations for this circuit. Now, once I know this, I can easily derive all the other ones. And you should be able to too. Don't just try to memorize equations. Okay? And that's what I expect you on an exam. So on the equation sheet, I'll probably give you this equation. If you divide by C, you'll get this equation. Okay, so you should know how to get from this one to this one, get this one, and then, or use that equation. You should be able to derive those easily. I don't expect you to derive this on the exam. That takes a little while. Okay. Now, the other circuit we looked at is, let's say we have a power supply, a resistor. We'll put a switch here. Let's see. Put a capacitor here. So this is switch S1, this is switch S2. So I leave that switch open and I close this switch. The capacitor charges up. We wait a long time. Capacitor is fully charged. No charge is flowing in my circuit. Then what I do is I open the switch and then I close this one. And what's going to happen? Well, if this is charged, and I have basically I have a complete path. I actually have an electric field in the wire. Charge is going to flow like this. In fact, the electron's going to go this way. Sorry, but the electrons flow this way, but the current's this way. Okay. The flow of electrons is this way, but the direction of I is this way. Because I is in the direction of the electric field. And so charge will flow. This thing will discharge. And the rate at which it's discharged, or the equation that represents the charge in the capacitor is a function of time in this case. Looks like this. Which R do I use in this case? R1 or R2?
R2?
Yeah, I use R2 because the capacitor is discharging through R2, correct?
Correct.
Can you remember an example where I actually did this in class?
Was this with that one special old light bulb?
Yeah, with the flash bulb and
Yeah.
the big capacitor. Yeah, I did. And I did it with the little light bulb too. So that's the example of a discharging capacitor. Okay. Yeah, the old flash bulb. They're not used anymore. So this is the equation for Q. And then, of course, if I want I, it's going to be dQ over dt. And when you take the derivative, you'll get a minus sign, and that's because of the fact that the capacitor is discharging. Okay. Because when this thing was charging up, the current through here was in this direction, right? The fact that the dq dt is negative is telling you that it's losing charge. So those are what we covered last time, and so what we want to do is apply these to a couple of problems. One thing I haven't discussed yet is the energy. So actually, before I do the problem, I just want to remind you that the only time you use these equations are when you're solving for something given time, the value for t. Or you have to solve for t given some value of v or q or whatever. All right. If you can avoid using the time equation, then do it, because that would mean that I only need to use maybe the voltage law or Ohm's law. Okay. And what happens on exams is I'll have problems where students don't need to use this equation, and they spend way longer solving the problem using this equation than just using the basic concepts. Okay. So my goal is to make sure that you get the fundamentals down and not just plug numbers into an equation right away. Okay.
All right. Professor?
Yes.
So for the Q equals Q max 1 minus e to the negative t over RC.
Yeah.
We're using that equation when the capacitor is being charged up, correct?
Correct.
And then the one without the 1 minus is when it's discharging?
Correct.
Okay. Okay, thank you.
Yeah, and if you think about it, if you get mixed up as to which equation you should use, when a capacitor is discharged, what should the charge be on it at t equals infinity?
0?
0. So which one of these goes to 0 at t equals infinity?
The one on the right side?
Yeah,
Left
so
side?
that's how, those are the things I want you to think about, right? I want you to think about it that way. So you can figure it out by saying, oh, at t equals infinity, my charge is 0, so only this equation satisfied that, so it must be this equation. Okay, so what you're doing is using your knowledge of physics there. Okay, so that's what I'm hoping students do, because I'm trying to get away, and I try to get away from students just focusing on the equations and understanding conceptually what's going on. All right, so we're given, let's say we have an RC circuit that's being charged by a battery or a power supply. By the way, the order of these two doesn't matter, okay, when I draw my circuit. So the first question I want to ask is, calculate the energy delivered by the battery in charging the capacitor. So I have a switch here. I close the switch. Capacitor charges up. What is the energy delivered by the battery? And of course, I can just tell you it's going to be Q max times delta V, but I want to do it a different way. Okay, I want to use the equations that we've used so far. What is the rate in which energy is delivered by the battery? That means power. Well, power is going to be the current times delta V sub S, which stays constant. So what about the current? Well, the current is going to be delta V sub S, and I erase the equation, over R e to the minus t over RC. If you take the equation for the charge and take the derivative of it, you'll get this expression. And this is the rate at which work is done by the battery. And so dW is P dt. And so this is going to be these two combined, delta V sub S squared. So this is the dW, but I want W, so I have to integrate this. What are my limits of integration? Well, obviously, I got to start at t equals 0 when I close the switch. But how long do I have to wait till the capacitor is fully charged? In theory, an infinite amount of time. All right, let me rewrite this. All right, so this integral is not hard for us to do. You're all experts in integrating that. When I integrate this, I get a constant minus RC. When I put the limit at t equals infinity, e to the minus infinity is 0, and then e to the minus 0 is 1. And so what I get is C delta V sub S, which is also Q delta V. That's the amount of energy that's delivered by the battery. And we talk about this in chapter 26. Half of that energy goes into charging the capacitor. So when this is fully charged, the charge on the capacitor is that. So half of the energy is lost. Where does it go? The resistor uses it up. The resistor acts like friction does in mechanics. So the next thing to do is let's prove that half the energy is lost by the resistor. Okay. This is the work done by the battery. Half of it will go to here, half of it will be used up. So what do? Let's calculate. The energy lost by the resistor. Okay, so what is the power, the rate at which energy is lost by the resistor? Well, that's just I squared times R. Okay, the current through it is I. So I squared times R is the power that's lost by the resistor or used up. And so this is going to be delta V sub S over R e to the minus T over RC squared times R. And this will give me delta V sub S squared over R e to the minus 2T over RC, because if this is squared, this 2 comes inside the exponent. And so P is dW sub R dt. So dW sub R is P
But
sub
Professor,
R. Yeah?
wouldn't the R have canceled?
This is squared though.
Yeah, but that's just. Oh, you're right. Okay.
Because I got a square every term here, right?
Yeah, yeah.
Okay, so get this. And so now I got to integrate this from 0 to infinity. I don't want to erase this, although I'm running out of space. Let's see what I can do. Okay, so W sub R is the integral from 0 to infinity of delta V sub S squared over R e to the minus 2 T over RC dt. Let me pull out the constants. Now when I integrate this, I'm going to get minus RC over 2, and then so the first term here, the one at infinity, gives me 0. The second term here, you have 1. And so W sub R and so this is the energy lost by the resistor. Half of it's lost by the resistor. regardless of the value of the resistance. Okay? So the difference between this guy and this, the difference between these two is how much charge is on the capacitor. We're okay with that?
Yeah.
Okay. It's kind of nice to show that. All right, so the last problem I want to do for this chapter is kind of a long problem. It's probably, I mean, to me, it's a very important problem. I like going over it. We covered these the other day. Is this one? And I'm going to be looking at the extreme cases for the most part in this problem. So watch how many times I use the time-dependent equation. Okay, I won't use it very much. So let me draw the circuit.
Hey, Professor, could I actually ask a quick question about that problem that
Sure.
you just erased? So it's more general, but anyways, if you have a power supply, a capacitor, and a resistor, just those three in a circuit, then you just know, or like through your derivation, you know that half of the energy is going to the capacitor and half of it's going to the resistor?
Yeah.
Okay, and does that vary if you were to like add resistors or capacitors, stuff like that?
So whatever the effective resistance is,
Mm-hmm.
the energy will go to the effective resistance.
Okay.
Yeah, it's irrelevant what R is, the total R is, right?
Uh-huh.
So
And like how many of R there is, or like how many resistors, it would still be, that still doesn't matter?
no, so whether you have, you mean in series?
Yes.
Well, whether you have one resistance with the equivalent value or 20 resistors that add up to that value, it's not going to make a difference. It's the same value.
Oh, okay.
Right.
Okay, I see what you're saying. Thank you.
Okay, so let me draw this circuit. My problem is the limitation of space. And I have a switch here. This is 9 volts. So I have a series of questions I want to answer. First thing is, I close the switch. What is the current through each resistor at t equals 0? So let me close the switch, and I'll use a different color for the switch. This might be hard to see, but anyway, I close the switch. I want to know what the current is at t equals 0. So what I'm looking at is at t equals 0 and t equals infinity. Before I go on, I want to write down the equation for the charging capacitor. I rewrote it using the distributive law, okay? So there's two parts to it. There's one where there's a time-dependent term. This is called a transient That's the transient term, the time that depends on, the term that depends on time, the transient response. And if you wait long enough, this term goes to 0. This term is the steady state term. Because this is the current, or this is the charge in the capacitor when t goes to infinity. So this is the steady state, and this is the transient response. This is the time-dependent part. That makes sense? So you're going to hear the term steady state and transients. When we get to chapter 32, you'll see that again. Okay? And when you take 215, you'll hear that term again. So this is the transient response of the system, and this is the steady state when t goes to infinity. And really, what that means is there's no the net energy of the system doesn't change at this point. Okay. So just some terminology. So we're going to be looking at the steady state cases in this problem, or the beginning. So I want to introduce these terms just to make sure if you never heard of them, just define them. Okay, so I want to know I want the current through each resistor t equals 0. So my first question is, when I close a switch, how does the capacitor behave?
Doesn't it start charging?
Yeah, when it starts charging, what does the capacitor behave like? I mean, if I draw my basic RC circuit, my current looks like this. I'll get out of the way. As the capacitor is charging, the current has this form. So if t equals 0, I equals delta V sub s over R. This is actually the maximum current at t equals 0.
So does it just act like it's not even there, like right at first?
Yeah, let's be careful what we mean by not even there.
Well, the current just goes right through it.
Yeah, so it acts like a wire, right?
Yeah.
And that's what I was trying to get at. This is at t equals 0, it acts like a wire. What about at t equals infinity? Because you said it acts like it's not there.
Doesn't like it stop the current from going through?
Yeah, in this case, there's nothing there. You have a gap there.
Yeah.
Okay. By the way, when the capacitor is charging, well, I got to be careful when I say this. Let's say I have a vacuum between these two. Really what's happening is that the plates are charging, right? There's nothing going through here. Right? There's nothing going.
You said this at t equals 0 or t equals infinity?
Well, as it's charging.
Oh, okay.
Right? As charge builds up on these plates, there's no charge going through these two plates, right? Going between these two plates. Okay. Yeah, when we say that there's a current through the capacitor, that's kind of a misnomer because it's really the charge is building up on the plates. Now, of course, if you have I'm sorry, go ahead.
No, it's okay. You keep going.
If you have a dielectric in there, of course, there's charge moving in there, right? Because the dipoles are forming in there.
Uh-huh.
So, but the charge is not really going through it. But there is charge moving in the dielectric. Because you're starting to form those dipoles. I'm just trying to be cautious with the wording, but okay. So right now it acts like a wire. So let me redraw it. And let me see. I'm trying to find my good marker. It disappeared. Oh, here it is. I'm going to redraw the circuit at t equals 0. So my circuit looks like this at t equals 0. That's what it looks like. Okay, because the capacitor acts like a wire. So I have these two in parallel. And I got a common denominator. So our equivalent is 2.5 kilo ohms. So let me redraw my circuit. So that's my circuit. And of course, the current is easy to find because these two are in series. So the total current is going to be my 9 volts over my total resistance. It's 9 divided by 14,500, and that gives me 621 microamps, or 0.621 milliamps. So the battery at this point is delivering 621 microamps. And so there's 621 microamps going through this resistor. And then it splits into two parts. But I want to figure out what this one is and this one is. So how do I do that? Well, let me redraw this circuit. Since these two are the same as this resistor, I mean, these two are in series, both of these resistors have this much current going through them. The voltage across this resistor is just a product of these two. And for some reason, I never calculated this value. So the voltage across these two is this value, whatever that comes out to be. Okay? So this replaced these two, which were in series, and so, in parallel. So the voltage across this one is also going to be
That voltage is 1.55.
Oh, thank you. Okay. Okay. So if I take the 1.55 volts and divide it by 3,000 ohms, that'll give me the current here. It'll be 521 microamps. Yeah, I have the voltages. I have the currents down, but not the voltages. So if I take this divided by that, I get 521 microamps. So if I take the 1.55 volts divided by 15 kilo ohms, I get, this is 517. This is 104. Let me double check. Yeah. So it is 104 microamps. This is 517 microamps. And the sum of these two has to be equal to that, according to the current rule. Okay, so I have the currents at t equals 0, but it's only though they only have these values at that time. What about t equals 1 second or t equals 2 seconds? Then what? Well, I have to. Then this is part B. If I want to know Q is a function of time and I is a function of time, well, I is dq dt. Then what I have to do, I have to apply KVL and KCL, Kirchhoff's voltage law and Kirchhoff's current law. I have to apply them. I have two loops here. I1, I2, and this is I1 plus I2. Okay, I have two loops, and I apply the voltage law, and of course I applied the current law there. And I have to solve for Q as a function of time and then take the derivative. And I did this, I'm not going to do it here on the board. And just to give you some examples, I solved for the current through that resistor as a function of time. And I got actually I got these two, sorry. I got that. And this is microamps. And then I15 I got as oops, I did that wrong. Okay, and the sum of these two is that. So that's what I got for the currents, but it takes a little bit of work. You actually have the math, you folks have the math background to be able to solve this. Okay, so you'll end up with a system of equations, and this one ends up being a differential equation. Let me think about this. Yeah, this one's a differential equation. This one is not, if I remember correctly. Okay, so you get a system of equations, and one's differential, but they're separable, and you can solve them, you can integrate them. In fact, later on the semester, you'll do a problem in the homework where you have to apply this. You have to solve something like this, but it's not with capacitors in it. Okay.
Hey, Professor?
Yeah.
For that I3, in the exponent, that's 10.34?
Yes.
And that comes from the 1 over R times C?
Yes.
So that's the resistance of that resistor times the capacitance of the capacitor?
No, it's a combination of things. It's not just the R times C of that.
Oh, okay. Is it the R of the whole circuit?
Yeah, it's hard to say. I forget exactly what it came out to be. It's not the equivalent R because you have a capacitor in there. I'd have to look it up. Hold on a second. Let me see what I did. I have my work here, but it's going to take me a while. Yeah, I didn't solve it in general because it was a mess. But if I did it in general, I put the numbers in. So I don't know exactly how the R's combine to give you R's and the C's combine to give you this. I couldn't tell you off the top of my head.
Okay, no worries.
Okay. But yeah, it comes from when you solve the coupled equations, you get that in the exponent. Let me check the chat real quick. Okay. Yeah, and in fact, I put the RC, this is the 1 over R. I would call this the 1 over R effective times C, whatever that turns out to be for that circuit. It's hard to say that because the capacitor's there, right? Okay. Anyway, that's part B. So I won't ask you to do this problem on the exam because it would take you the whole class period to solve it. And like I said, you guys have the math background to do it. It takes time. And when you do the homework problems, I think they're in either chapter 31 or 32, you will actually do this in one of the problems. Okay, there wasn't one in this chapter, so I didn't assign it. Okay. So the next question is, what happens, how do I answer the question regarding the current if this guy's not there? This is the thing that screws everything up. Okay? Because if you take this, if you just replace that with a wire, this is a really simple circuit. Because the voltage drop across the resistor is the power supply voltage, if there's no resistor there. The voltage drop between these two is the power supply voltage. It's like you have two circuits. It's like you have two separate circuits, one with a 9 volt and a 15 kilo ohm resistor, and another one with a 9 volt and this RC circuit. And so the total current is the sum of this current, which is constant, plus the sum of this RC circuit that's hooked up to a 9 volt supply. That's it, because the voltage drop is constant. It's as if you have 9 volts across this, and the total of 9 volts is constant. So if this resistor wasn't there, this problem is much easier to solve. You can essentially write down the total current, because it's going to be the current through here plus the current through here. It's the current through a simple RC circuit plus the current through his 15 kilo ohm resistor. That's all you got to do. Okay, so it's pretty straightforward when this is not there, but you throw this in there and it makes life a mess for you. Okay. Now, the next question is, what is the steady state current in each resistor? So let's erase these. I want to know the steady state current. Now, what does it mean, steady state? It means that I wait till t equals infinity. And when t equals infinity, then how does my circuit behave? Well, how does my capacitor behave? Well, it acts like an open circuit. So basically, I have this. That's what I have. There's nothing here. And so the voltage drop across here is 0. So if this point is 0 volts, this point is 0 volts, and so is this point. This point is at the same potential as here. So that means that the voltage drop across this resistor is the same as whatever the voltage drop is across the capacitor. Because one end of the capacitor is at V, the other end of the capacitor is at 0. So that's my circuit. There's no current going through here, except there's a voltage drop across the capacitor that's equal to the voltage drop across this thing. Basically, my circuit is this. So when you look at this, the current is going to be 9 divided by 27,000. Which is 333 microamps. So look at this equation when t equals infinity. What do you get? You get 333 microamps. When t goes to infinity for this one, I goes to 0. It's because you have an open circuit here. So I have 333 microamps going through this resistor and this resistor at t equals infinity. Now the next question is, what is the charge?
Hey, Professor?
Yeah,
So the current through the 3 kilo ohms is just 0, right?
it's 0. Yeah, so I is 0 for
cool.
this one. I'll write it here.
When t equals infinity.
Yeah. And that agrees with this equation, with the one that I derived. And then I have agreement with this equation because when t goes to infinity, this term goes to 0. I forgot the microamps here. Okay, so let's put the capacitor here. What's the charge on this capacitor when it's fully charged? Well, the voltage across this capacitor is the same as the voltage across that resistor. So there's 5 volts across here. This points at 5 volts. This points at 0 volts. This points at 5 volts. That points at 0 volts. So Q capacitor, Q max, is going to be 10 microfarads times 5 volts. 50 microcoulombs. So there's 50 microcoulombs on that capacitor. Now, let's say I open the switch up. What's going to happen when I open the switch? Well, when I open the switch, this capacitor, which has plus charge here and minus charge here, the electrons are going to want to go this way, which means that there's a current Let me get rid of these. The switch is open. Current is going to go like that. The capacitor is going to discharge through both of these resistors. So my circuit then, my equivalent circuit, when the capacitor is discharging, really is this. Oops. Okay? And then I can replace it in the following way. Those two resistors are in series. Q max was 50 microcoulombs. So the way this discharges is this way, given by this equation, where R is 18,000 ohms and C is at 10 microfarads. Okay? The question asks, how long does it take for the capacitor to have 1/5 of its charge? When is Q equal to Q max over 5? And I don't have to put numbers in. The Q maxes cancel. 18,000 times 1 times 10 to the minus 5 is 0.18 seconds. And then what do? I take the log of both sides. And then I'm going to do a trick with the logs. I'm going to get rid of the minus sign by flipping this over. And so T so in 0.29 seconds, it has 1/5 of its original charge. By the way, I can write the current for this. Where I max is the 5 volts divided by, because this was originally 5 volts. So boy, I've gone through every aspect of this problem. And this is really the only time I looked at the time-dependent part. Okay? So understand how the circuit works at the extreme cases. Make sure you know how to solve this problem. Okay? Make sure you know how to solve this problem. With or without that resistor there. So I'm going to spend a few minutes, because I'm done with the chapter. And I'm hoping a lot of people are doing the problems at the last minute, the homework problems, which is not a good thing. I wish folks would do about 3 or 4 a night. Anyway, it just helps you to learn the material better. I want to ask you folks a couple of questions. And granted, there's only 2 of you here. 3 of you, sorry. Let's see if I can find some nice questions. I asked the group yesterday. I'm going to ask you the same. I'm going to ask this group the same 2 questions I asked the other group. Let's see. I'm going to launch a poll, and you can't see the question yet. Hold on a second. You can all see the poll, right?
Yeah.
Okay, so here's the question. Rank in order from brightest to dimmest the identical bulbs A through D. So all the bulbs in that circuit are identical. I want you to tell me which one's the brightest and which one's the dimmest. So I'll give you a couple of minutes to think about it, write down some equation. Or you might be able to answer it conceptually, just think about it in your head. If not, draw a picture, try to solve the circuit. far no one's chosen an answer. This was kind of related to that demo we did the other day. Okay, everyone's responded. I'm going to end the poll. I'm going to have you guys. Everyone chose the same thing. So does anybody want to explain their answer?
I mean, I guess my reasoning was that A would be the brightest because it doesn't have any resistance before it. C and D, because we often treat resistors that are in series as the same. Like we can combine them into one resistor. I considered those to be equal. And then I was actually debating between B and D because I wasn't sure why B would be brighter than C and D, but I guess it doesn't have any other resistor, but that's my reasoning.
So it's true, A gets all the current, right? A gets all the current from the power supply. Then it reaches that junction and it gets split into two. In fact, since you have more resistance with the two bulbs, B is going to get more current than the other two,
yeah.
right? And not only that, those two bulbs are in series, and so they're going to have half the voltage drop that B does.
Yeah.
So yeah, that's right. So the answer is B. Okay, good. So I'm going to ask you one more question. So we have this circuit. You might have to draw a picture. This might require a little bit of work on your part. So here's a circuit, and the person who drew this picture did not apply the current rule right away. But the question is, based on those current designations, which set of equations is correct for describing the sum of the voltage drops in the loop containing E2, R3, E3, and R2, basically the loop on the right? Which of those equations? So what you're going to have to do is write down an equation. You have to sum the voltage drops. And so I just want you to go through some of the voltage drops and then see which one of those equations matches yours, if any. So I'll take a minute or two. And while you're doing that, I think I'm going to draw this picture on the board. Okay, so, everybody solved it already, okay. Oh no, one more person, sorry. Okay, everyone's answered. And again, you're all in agreement. And I want to end the poll. So what I'm going to do is I'm going to sum the voltages. I'm going to go clockwise. Just for fun. Okay. I can go either way. I can go clockwise or counterclockwise in summing the voltage drops. But let's go clockwise. So let me start over here. And I go this. I'm going in the direction of the current. This is going to be a voltage drop. Then I hit this power supply. That's a voltage gain. I go around here. I'm summing in the direction of the current. And then I got another voltage gain. So that's my equation. And which one of those equations matches my equation?
That'd be D because they're all the signs are flipped.
What do you say mine matches D?
Yeah, I mean, if you add everything and subtract everything to the other side, then all the signs will change, or just divide by -1. It's the same.
So if I summed the other direction,
Yeah.
it would match D. So you're right. I mean, basically, I purposely chose this one. I wanted to see if you guys noticed that. But yeah, I summed clockwise, and really, this matches D. If I multiply through by -1, which means summing the other direction, it'll match D. You should be able to eliminate B and C because no matter which way you go, these voltages are going to add, right? If you go this way, they're both gains. If you go this way, they're both drops. And so B and C has the two power supplies, the voltage drops of the two power supplies of opposite signs. So you could eliminate B and C right away. And you say, oh, it's either A or D. Okay. And then you can eliminate A because the voltage drops will have the same sign for these two. Okay, good. All right, so I'm going to take half an hour today just because I just need to do one thing. So let's take a break for half an hour. We'll meet at 12:50. That sound good?